Whoa, that's way too bright. That's good. Wait. Let's see. Good old standby. There. There, just hold it. Okay. Give it a talk like this. I think I'll stop fiddling with that. Alright, there we go. So, welcome back. Mic's on, right? Yep, okay. Welcome back to Tomography. So, I apologize for being so slow with getting lectures out. A lot of these take like days for me to put together, and finding exactly the right amount of time, the right times to record has been fairly difficult lately. I just ate dinner. Anyway, yeah, so it's late tonight, and just trying to get something recorded for you guys. I have already recorded the lecture over several days, so this is going to be talking about what are called algebraic reconstruction techniques. So up to now, what we've been working with is sort of continuous reconstruction techniques, and we've pretty much finished them. We talked about the Fourier transform, back projection, Radial Transform, discrete versions of all these guys, and we talked about filter back projection. And filter back projection is how you do it. That is how you go from a sinogram to the attenuation function. And yeah, and after that, having filter back projection, it really just comes down to various geometries of scanners and to putting things back together. Yeah, so at this point, you pretty much know more or less the state of the art. I think this is what is used in most CT scanners, although there are other numerical methods. And so some of the methods I'm going to talk to you about today are the ones about them. And so this is an approach called algebraic reconstruction techniques, where basically you treat you express your attenuation function as a collection of bases, as a sum of basis functions, and usually we're just thinking of these basis functions as individual pixels. And so then you're trying to figure out exactly the height of that pixel, you know, based on some constraints. These constraints come from the Radial Transform, where we know that if we integrate through a bunch of these guys, then the weights on each one of these pixels has to be, you know, so along this line has to be such and such to match up to give you the interval, which is where you got from the sensor. And so so this sets up like a whole different approach to doing reconstruction, and it's maybe a little bit more basic and a little bit more direct of a problem, but it doesn't work as well as the filter back projection. The filter back projection itself builds in a whole lot of filtering, which is really handy for handling noise and other things, and it's harder to do that with these algebraic reconstruction techniques. But they're classical. The first CT scanners had used was we call now the Kaczmar's method. I can't pronounce his name, and which Kaczmar didn't actually use it for CT. It was sort of he was doing it to just solve equations of the form AX equals P, where A is a matrix, X is an Rn, and P is in, say, Rj. And so basically, it is a general linear algebra numerical solutions technique. It isn't a great technique. There are definitely better ones, but it does what are called affine projections, and so you start with a guess, and then you take that guess and you basically take a look at each row and make a line in the plane, and then you project your guess onto that line, and then you continue, or a sort of a hyperplane sometimes, depending on the dimensionality of the problem. And so then after that, that gives you one solid method of doing algebraic reconstruction techniques, but there are other ones, and so we can look for other ways to solve ax equals p, and another really main one that is used a lot in data science are pseudo-inverses and also least square solutions, and so we'll talk briefly about those. But then after this, I would like to use this as a jumping point to some of the work that I do in dynamical systems, which leverages a lot of these tomographic ideas. And so my work is a lot closer to this idea of algebraic reconstruction, and so it's a good segue to get in there. Now, for getting to the point of talking about my own work, that's going to be a lot easier for me to record. I can rattle that off the top of my head, and it takes almost no planning for me to jump in and do it. Whereas with this, I always have to go and study the book for a few days and get my head into the problem before I jump in. This one ended up being kind of a convoluted hodgepodge collection of results, and I apologize if it makes anything confused or I stumble anywhere. It's been a busy week, and there's been a lot of change in routine lately. So anyway, yeah, I hope you like it, and yeah, I'll go ahead and start.
Okay, so at this point, we've actually been through the entire construction and sort of analysis that you would do for reconstruction using Fourier type methods. So we defined the Fourier transform. We have defined the inverse Fourier transform, the Radial Transform, and all of these things. And we showed that how they were all connected through the filtered back projection. And after we solved the filtered back projection, we realized that we can't use it in exactly the form that we see because it would end up amplifying too much noise if there was any noise in the system. And so often, so we saw several ways that we can develop low-pass filters to kill any sort of high frequency content, which is where the noise would live. So so now that we've done that, what we're going to do is we're going to go ahead and take a look at some other techniques. So these are generally fall in a category of algebraic reconstruction techniques. And to a large extent, in the CT world, these aren't actually used all that frequently. The CT scanners and CT software is generally optimized to do Fourier type methods, but this is important from a historical standpoint because the techniques like the Kazmark method was actually used in a lot of the initial CT scanners. And from a numerical linear algebra standpoint, this actually makes a whole lot of sense intuitively. On the other hand, often these algebraic reconstruction techniques are sort of some of the go-to techniques when you're developing a new kind of tomography approach. So this is, yeah, so it's good to know about this. And the actual algebraic technique isn't actually all that difficult, and so what we're going to be looking at is what's called the Kazmark algorithm. Let me see if I can figure out how to spell it real quick. Yeah, so today we're going to be talking about the Kazmark method. I have no idea how to pronounce that, so I'm just gonna continually screw up the name, and I apologize, to anybody who takes offense to that. And so this was developed just like the Radial Transform was developed well before the CT scanners. This itself ended up being something that sort of predated a lot of the CT scanners, and it was used in the initial CT scanners back in the 1960s. But it was developed independently there, and then later on again it was connected back. So let's go ahead and just sort of talk about this sort of problem from sort of a high standpoint. The Casimir's method isn't actually made to do CT scanners in particular, but rather solve a system of linear equations. So solves a system of linear equations, and it does an okay job. It isn't actually the best method for going about it. There are other methods that we can do, like least squares methods and things like that, which we'll also talk about. So let's go ahead and write that. Least squares. And again, this comes with the same sort of principle. It's a linear algebra technique. Basically to solve, or I think P is what we use in this case. So basically, and so least squares methods are methods for resolving the difference in the range. There might not be a unique solution for x, but we pursue the x that will give us the smallest difference between ax and p, where p is something that we're looking for out of our which basically represents our Radial Transform. Okay, so what is the general idea of algebraic reconstruction techniques? So essentially, we're going to have just an array of pixels. So this is a lot like the first sort of example that we went through back in in the first lecture. And so we're going to have a grid of k by k vectors, and so there's say k squared unknown pixels, and we're going to try to figure out what these pixels are. And so in order to do that, what we're going to do is we're going to come up with a basis. And so this basis is going to be like b, and that's little k on it of xy is equal to 1 if xy is in pixel k and 0 otherwise. So basically the idea is that we will just order these in sequence, so it would be like 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16, like that. And what we'd say is that say if this was 1 2 3 4 5 6, and we're taking a look at say b little b6 of xy, essentially if xy is in here, then we get a 1, and so like basically we're 1 here and we're 0 at everywhere else. Right. So this ends up being a basis for our pixels. And so basically what we're doing then is, if we're looking for the attenuation function, an approximation of the attenuation function fxy is going to be given this way. So it's a sum for k equals 1 up to big K squared of x of k times bk xy. Right. So then the goal here, that's x little k, is we want to find x little k. And so we generally think of x being a vector in say rk squared. Okay, so what do we do in order to get this? Well, if you take a look at the Radial Transform of f tilde t theta, I mean, it is a function. It's f tilde isn't going to be a continuous function, but it is a piecewise continuous function, where basically, it's, let me see if I can draw what I mean. So basically, it's a function that has a whole bunch of, that looks something like this, right? So, yeah. So it's a function that's sort of piecewise continuous. It's sort of a step function, something like that, right? And so, so this is x and this is y. And so this could be f tilde, for instance. And each one of these heights is represented by xk. So this is at xk, this height here. So, so we know at least we can take integrals over this. And in fact, we know that these integrals have to be finite because each element bk is only supported inside this little square. And so, and since this whole collection of bk is only supported on k squared altogether, we know that any values outside of here is just going to be 0 for Radial Transform if we're doing an integral. So, so we know that all the integrals are finite and they exist, and so there's no real question about that. So then if we take a look at the Radial Transform at t theta, just like we have been, this is the sum k equals 1 to big K squared of x of k of the Radial Transform of bk t theta. Right? And so, so then if we end up getting, so we know we only have a finite number of t's and only a finite number of thetas, and so so we have just like we were talking about with the discrete reconstruction. So we only have these guys. So say t1 theta 1 up to t j comma theta j, and for some positive j, and so essentially we're going to, for each one of these we have basically what we're going to have is we have these Radial transforms f tilde at tj comma theta j, and this is equal to p little j for little j equal 1 to all the way up to big J, right? And so so these are our samples. Okay. So now we can actually develop a system of equations. So what we have then is we have pj is equal to the sum k equals 1 to k squared of x of k times the Radial transform of our basis functions of tj comma theta j for little j equal 1 to all the way up to big J. Okay, so so then there's still one last unknown that we haven't really talked about. So so these are actually unknown. We're looking for these, and this is what we're getting from scanner, right? But this guy is the last bit that needs to be computed, and generally speaking, what you're going to do is you're just going to take a look at say, your point T and theta. That is horrible. There you go. So T and theta, and then you basically just need to compute through the square the length of this line. For say 0 width X-rays, this is straightforward. So but it does get more complicated if you don't have 0 width, because you need to take into account other bits. So generally speaking, we think of these as corresponding to 0 width X-ray beams. Okay, and so so then what we do is we go ahead and we set Rjk to be equal to the Radial Transform of bk at tj theta j, right? For j equals 1 to j, and little k going from 1 all the way up to, say, big K squared. Okay, so therefore we finally have a system of equations that we can properly talk about. So we have Pj is equal to the sum of little k going from 1 to big K squared of xk r jk. And this is for j going from 1 all the way up to capital J. Okay, so let's see. So basically what we need is, so we're turning this into a system of equations. Ax is equal to P, and A has to have as many columns as the size of x, and so in that case that means that we need x's size k squared, so number of columns k squared, and the number of rows has to match the size of p, and so this is going to be j times k squared matrix. You can say a real valued matrix if you want. We don't get any complex answers out of X-ray beams. Okay, so all right, so then the question is, is this solvable? And both computationally and practically. That's something we should talk about. And so, yeah, let's do that. Okay. So then the question is, how big is k squared, and how big is j? So as far as j goes, according to Feynman, and we are indeed following Feynman again, he says that a typical X-ray has 200. A typical scan has 200 X-ray measurements at 180 different directions. So 200 X-ray measurements at 180 directions. And so j ends up being 36,000 roughly. Well, let's not put the k so we don't get confused. So 36,000 size. And so then everything really comes down to, so put up here j 36,000. So everything comes down to k. For an image of say 160 by 160 pixels, this is going to be something of the order 25,600 pixels. Then in this case, we have an overdetermined system. That is, we have more measurements than the total number of unknowns, and so generally speaking, solvable theoretically. But so for an image, that is, say, 256 times 256. this gives us 65,536 pixels unknowns. And so we are very underdetermined. And so, so basically, you know, I can say not uniquely solvable. Or, well, not solvable. Potentially not solvable. Problems. Okay, so so we have an underdetermined system. You know, this is where we turn to things like regularization, and so we sort of augment the system matrix by adding a bit to, like, say, the least square solution. So we add lambda times the norm of W squared, and then that'll give us something to work with, even if it doesn't, you know, do a great job. It'll give us something. So, so yeah. But yeah, so okay. So then another thing to mention is that if we take a look at any individual line going through our array of pixels, something to notice is that only a handful of spots are going to end up having a non-zero contribution. That is the RKJ, which was the Radial Transform of BK at theta j TJ. Did I get that order right? TJ, theta j, right? Other way around. Non-zero for only a few points. In fact, generally on the order of k. So that means, you know, when you have this k squared sort of terms that you're trying to determine, most of it is going to be 0. So this is 0, this is going to be 0. And so even though you have like a whole, so even though each of these, you know, entries here, you know, for x1 down to xk squared, most of this is actually only going to be 0. So, you know, maybe have, this is all 0, 0, maybe have a few points that aren't, 0, 0, a few points that aren't, 0, 0, a few points that aren't. And so generally speaking, this is what your matrix looks like. And so, so this is what we call a sparse matrix. And generally speaking, k squared would be a sort of a nightmare to have a, say, 65,000 by 65,000 matrix. That would be a very hard problem to solve computationally. I mean, maybe you could do that in particular, but I mean, if you try to increase resolution even beyond that, you start to run into this really big bottleneck of computational problems. And so, and in particular, you have a big issue with storage. But the nice thing is for sparse matrices, you can go ahead and store only the non-zero values in, say, MATLAB and things like that, so it helps on memory issue. And it also turns out that there's a lot of matrix inversion problems that will directly take advantage of the fact that it's sparse, and so it'll reduce the number of operations that you need in order to solve the system. So, so generally speaking, if you're talking about a very big data problem, you are hoping that it ends up being a sparse problem. And even if it isn't, you find ways to try to sparsify it by demanding that certain parts are 0 versus others, and so forth. And so, so in this case, though, it naturally happens because we're taking a look at a single X-ray beam each time going through here, and it is only going to cross you know, a finite number of pixels. and so all those other pixels have to be giving a non-zero contribution. And a lot of this comes down to not only the X-ray beam, but the fact that we chose our basis functions in this way. So the basis function is only supported in this sort of area, and we call this compact support. And a lot of people also try to design algorithms doing that. If we put, like, say, a Gaussian here, it wouldn't technically end up being sparse. So instead of having BKXY, we have a Gaussian. Then we'll have definitely a smaller contribution outside of the region, but it won't be zero. Now, you could just sort of demand a sharp cutoff after a point, because the Gaussian does shrink pretty fast. But that is an extra consideration. There's other basis functions that do come up, and maybe we'll talk about it in a lecture or two. Things like the Wendland basis functions that are compactly supported and continuous, and etc. And so this will give us a sort of different perspective on doing a lot of these problems. Okay, so that's where we are now. So we sort of defined the problem, and we've sort of analyzed it from different perspectives. We have, for instance, talked about the basis functions. We've talked about how to set up the system of equations. So we have x, and then over here we have p1 down to pj. And so these are our samples, and this is our unknowns, and this is our matrix A, which happens to be sparse. And depending on the number of pixels that we really want to resolve, we may or may not have enough data. So these are all things that we need to really sort of reconcile. And there's a lot of variables to pick out. So you'll notice that for the method that used the filtered back projection, we didn't actually have to define how much what our pixels were, because the ultimate result we got was a function, and we can evaluate it at any pixels that we really feel like. But in this case, since it's an algebraic reconstruction technique, we actually have to define exactly how many pixels that we have, and then try to build off of that. So this builds in challenges of its own, and it gives you a bunch of parameters to play with, which can be good, but it's easy to make a system that doesn't have any actual solution. So, all right. So the next thing I want to talk to you about then is the Kasmark method, which would correspond to section 9.2 out of Feynman. And this is Kasmark's method. I'm doing my best. Okay, so this is a way of solving. Basically the goal is that we want to solve a matrix equation, AZ or AX is equal to P. And here x is going to be in r or k squared, and p is in the reals size j, and a is a matrix that is of size j cross k squared. Right, and we're going to hope that a is actually invertible. And in order to do all this stuff, we need to talk about affine spaces. Okay, so now what we need to talk about are these affine spaces, and so let's just go write it down. So affine spaces. So affine space is almost like a linear space. So recall, basically. If you have a sort of linear subspace of Rn, and you take a look at, say, like this subspace here, subspaces require a zero vector. So but what we're going to be talking about are spaces that we call affine, and so basically what we do is we end up shifting these sort of linear spaces up, and so this is what is called an affine set. So so an affine space corresponding to a vector r, let's say r n, and some p in the real numbers is given as this, and so as s r comma p is equal to all x inside of, say, Rn that satisfy x dot r is equal to p. So so basically you get some sort of linear term and then it's shifted, right? So if this was equal to 0, so if p was equal to 0, then that would be a linear space. But this is affine. So now it turns out we've been talking about a whole bunch of affine spaces, and so it turns out that L T theta defines an affine space. And so basically what we're going to do is we end up replacing r with cosine of theta comma sine of theta, and then we also set x is equal to say t cosine theta minus s times sine of theta comma t times sine of theta plus s times cosine of theta, and you know, for some parameter s. And so s basically will run through every value of this affine space, and then what you end up getting is you get r dot x is equal to say t cosine squared of theta minus s times sine of theta cosine of theta plus t sine squared of theta. My son's banging on the window. Hi, Isaac. Okay, so sorry, I ended up being distracted there. Plus s times cosine of theta sine of theta, and all of this can be broken down to t times cosine squared of theta plus sine squared of theta, and that itself is equal to t. So okay, so then you see that we end up having an affine space for all the points that are described by this affine problem. So this is our vector of, you know, usually we'd say xy, but in this case we're just considering x as being r squared. And so this defines all the points on the line, and as long as we you know, think of r as being cosine comma sine, like you would for any unit vector, then this is what you get. So you have this. And so that means that we have an affine space, you know, sort of in the direction of r. So yeah. And so in particular, you know, basically, you know, we have in the direction of r, yeah, this is theta and t, and here, and so this vector itself is actually going to be r times say t comma r, where t is a scalar and r is a vector. So and so that is the affine space that we're usually talking about. Okay, so we can also see a relationship between affine spaces and some subspaces, and you can even see this is actually going to be an equivalence class. If you don't know what equivalence class is, don't worry, we don't use that term in any deep way, but it's basically ways of equating different collections of elements. So basically we see that for any you know, r and p, we consider, say, s r comma p, and of course p is a real number and r is in, say, Rn, and also we're going to consider s r naught. So then if say x1 and x0 are in say SRP, and we define sort of this homogeneous vector xh as x1 minus x0, then we can see that r dot x1 minus r dot x2 is equal to r dot x1 minus, or sorry, x0, x1 minus x0, and so then this is r dot xh, and since both of these should be equal to p and p, this should be equal to 0. So thus we have our homogeneous equation xh is equal to 0. Sorry, it is in SR comma 0, right? And so, okay, so there we go. So then you can think of, if we fix R and let P range from say negative infinity to infinity, then the collection SR comma P is going to be a collection of equivalence classes of Rn. Okay, and so that's something that could happen. So if you look through, so if you end up looking at Feynman's text, here I'll go ahead and. Okay, so this is an example from Feynman, and this is his figure. So Feynman figure. So just give credit. But yeah, basically the idea is that he's trying to solve this system: x plus 2y is equal to 5, and x minus y is equal to 1. And so so he has 1, 2, 1, negative 1, xy is equal to 5, 1, right? So this would be his p, this is his, x, here's written as xy, and this is his a. So this is a very simple system, and even though there is actually a unique solution here, when you run Feynman's method, so you end up getting these points here, 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 and here. Actually, this one does end up converging. It gets pretty close. So this one's good. But if you look at the third one, it's an inconsistent set of equations. So we have 5, x minus y is equal to 1, and then we have another one, 4x plus y is equal to 6. Well, there is no solution that satisfies all of them. I mean, that's just life, right? So 1, 2, 1, negative 1, and then we have 4, 1. And then we have x, y. It's just two variables, so x and y is equal to 5, 1, and 6. And so there's not going to be any x and y that satisfies all three of these at the same time. And so what you see then is that the solution ends up settling into this triangle that goes between them. And so you might, so in this case, we know there is no unique solution. And so finding x and y might be difficult, but the, in fact, impossible to satisfy all those. But the, but you might not know that. I mean, this one's pretty obvious. It's not, there's no solution. I mean, you just look at the graph, right? And there's no point that satisfies all three of those lines.
And so, but on the other hand, given a random matrix, or a matrix that you get from data, then, I mean, you don't know exactly, it won't be as easy to visualize that this is going to be a problem. And so, so you might run into some of these issues there. Okay, so, but there is a theorem, this is Theorem 9.6, and it says that if the linear system AX equals B has at least one solution, then the K method converges to a solution. So and then they say, moreover, if X naught is in the range of A transpose, then K method converges to the solution of minimum norm. Right, and so this sort of thing would end up happening if, so if your system is uniquely solvable, then it converges to the solution. There would only be one solution to converge to, and Theorem 9.6 tells you that it works. In cases where you would have at least one solution or more than one solution would be when you have a non-trivial null space of A. And so in the case when that does work, if you start with X not being in the range of the transpose, then that means that the K method would converge to the solution of minimum norm. One way to guarantee that X naught would be in the range of minimum norm is just take a vector and hit A transpose against it, and then use that as the your starting point. But yeah, so so anyway, so that'll give you that. So so this is the theorem, and it's nice, and so it sort of validates the Kazmark method, which does all these like projections, affine projections against all these rows. So it's sort of trying to fix each value of X one at a time by like forcing it to match up with the row, and so it turns out to be a fairly decent method. There's a couple of variations that you can do with the Kazmark method, and I'm not going to prove this theorem just because we don't really have time in the class. I'm trying to cover a few more topics before the class is over. And so there's some other variations we have of the Kazmark method. So Kazmar's, and these come through like what would be called relaxation parameters. And so so basically for for each I and j, we're going to let say lambda sub jk satisfy, well, we'll just say be between say 0 and 2, non-including. And then you can replace the Kazmark method with this guy. So basically, these computations of x to the k comma j becomes x to the k comma j minus 1 minus lambda jk times and then the rest is just a projection formula. X to the k comma j minus 1 dotted with rj minus pj. And then divided by rj dot with rj, comma rj, times rj. And so then this is a relaxation version. And so with lambda jk equal to 1. This is the original method. And yeah, so this gives you a way of doing it. And the book also talks about a couple of other ideas where the projection is actually wiggled a little bit, where you start thinking of r.x actually living between, or rj.x living between some distance of epsilon of pj, where you're not requiring that it matches it exactly, but you know, but you want it to be fairly close. So yeah, so there you go. Okay, so yeah, so therefore, you know, we have the Casimir method is fairly straightforward, and I mean, and if it wasn't clear before, basically what we're doing is we're trying to look at ax, and we have, say, r1 down to rj times x is equal to you know, wherever p is. And we know that pj then must be explicitly written as rj dotted with x. Yeah, just because we know we take rows and multiply it times columns, and that gives us each one of these entries. And so what's basically going on here is that we are taking a look at sort of the affine space here, and we're forcing this x to, you know, adjust to live on this one, on this particular space, on this affine space, and but then on the next one we match a different affine space, and et cetera, et cetera, et cetera, and hopefully, I mean, you know, it'll end up converging eventually, but yeah, it's but we saw that sometimes it can lead to you know, loops and other things like that. And it's an approximate method, so you do it once and then you match them all, but you know, as you match the first one and then make adjustments for all the subsequent ones, you can screw up that first match, and so then that's why you rerun it, and hopefully, and the idea is just by iteratively doing this over and over again, these matches stop disrupting each other too much, and then they end up converging, and so yeah. So now let's go ahead and we'll talk about sort of least squares solutions. And yeah, and we'll do that. Okay, so there's one last thing I want to talk about. So the book has an excellent discussion on the singular value decomposition and how to actually work with it, and if you're in the face of a whole lot of like zero eigenvalues and things like that, you can use a truncated SVD. So I'll just say, you know, SVD and truncated SVD discussions in the book. These are you know, very good tools to know about, but before we wrap up, I wanted to talk about you know, what is called Tikhonov regularization. It only takes like a second to really talk about this. So generally speaking, sometimes you know, say A transpose A is not invertible, or you know, it's numerically has poor conditioning.
So you could be invertible, strictly speaking, as a matrix, but but numerically, rounding errors and other things like that could build up. And if it's a very sensitive matrix with respect to its condition number, those small changes will lead to big problems. And so there's another method that you can do in order to resolve these sort of algebraic problems. And so, for instance, you can take a look at the minimum of, say, ax minus p squared, and then add on this regularization term. And so this ultimately will lead to this algebraic equation, this normal equation, where you have where you end up having, say, A transpose A plus, say, lambda times the identity matrix times x is equal to p. And if A transpose A was not invertible, well, we know that A transpose A is a positive matrix, and just symmetric, and etc. So then basically we bump up all those zero eigenvalues a little bit by lambda, and so it sort of buoys our matrix up. But of course, this is a not an exact fit for say ax equals p, but maybe we had a lot of noise, or there's problems where it's overly sensitive, and so is sort of the it is the regularized solution to this, using the Tikhonov regularization, where that is, the regularization is adding this, and usually we say for some lambda positive, hopefully small. And so, generally speaking, you just pick lambda to be like 0.01 or 0.001 or something like that, and then you increase it from there to see when you start getting some sort of credible solution. So this is another approach to resolving this problem, and this is called a regularized regression problem. Sort of heuristically, if we look at this, we can see that since we added the norm of x into our minimization problem, this is also sort of saying, let us get the best fit we can here without letting x become impossibly large. And so, this can help with that too. Okay. So with that, you have a whole host of different approaches to solving this algebraic approach to image reconstruction, and in MATLAB we can take a look at that in another lecture. But this gives us a whole bunch of little tools to play with. We can try the cast-marked method. We can try the pseudo-inverse method by solving the least squares problem, like what I just talked about, and then we can also try the Tikhonov regularization. And then next, I would like to start diving into some of the concepts that come up in my own research, and this is with doing things like kernel approximation. And then we'll talk about some applications of tomography inside of dynamical systems. But we are also, I owe you a few lectures on just performing all this stuff in MATLAB and putting it together, and taking a look at this stuff. All these algorithms implemented. Now we finally have a collection of reconstruction techniques. We should see how well they work. Okay, well, thank you for listening, and I think I'm going to call it here. All right, bye-bye. Okay, so now you have another tool in your arsenal for inverting the Radial Transform, or inverting from sonograms. We will later have a lecture or two just committed to trying out these algorithms and doing different things, and this week I'll be sure to give you guys a formal project to go play with. A lot of this will really just come down to breaking open the Radial Transform, or the Irradon function in MATLAB,
and tweaking certain things to see what we can get out of it. Of course, don't modify your own radon without making a duplicate, but we'll get there when we get there. Anyway, thank you for listening, and I'll see you next time.